In this video, we'll take a look at another example of a hypothesis test involving a population proportion. This example is also similar to exercises 15 to 26 in section 10.2 of our textbook. It has been estimated that worldwide about 32% of tree squirrels are left-handed or left-pawed. A biologist for Yosemite National Park believes, however, that the rate, or in other words the population proportion, of left-pawedness among tree squirrels in Yosemite Valley is higher than the rate of left-pawedness among tree squirrels worldwide. The biologist observes a random sample of 125 tree squirrels and finds that 54 out of the 125 tree squirrels are left-pawed. Is there sufficient evidence to conclude that the rate of left-pawedness among tree squirrels in Yosemite Valley is higher than the rate of left-pawedness among tree squirrels worldwide, using alpha of 0.01 as your level of significance? So as was already noted, in this problem the word rate is used a few times, and rate is the same as a proportion, and all of these in particular refer to a population proportion. So in your homework or on a quiz or test, if you see the word rate, keep in mind that that just means proportion. For the solution, our first step is going to be the initial step of step 0, summarize the information and identify the point estimate. This step is optional, but I think it is helpful. So in the problem, it mentions that worldwide the proportion of squirrels who are left-pawed is 32%, and this biologist examined the squirrels in Yosemite Valley. This biologist took a sample of 125 squirrels, and in that sample 54 of the squirrels were left-pawed. So that sample proportion for Yosemite Valley comes out to x divided by n, so 54 divided by 125, which is 0.432. The sample proportion for left-pawedness among squirrels in Yosemite Valley, 43.2%, what we calculated up here, is higher than the population proportion for left-pawedness among squirrels worldwide, which was 32%. So this seems to support the biologist's hypothesis. However, we will need to test whether that sample proportion from Yosemite Valley, the 43.2%, is significantly higher, and if it is, that would be sufficient to support the biologist's hypothesis. The first step is state the hypotheses. This is another hypothesis test involving a population proportion, and we'll use P to represent that. And in particular, P represents what is unknown in this hypothesis test. And the unknown in this test is the population proportion, or the rate of left-pawedness among tree squirrels in Yosemite Valley. What is known is the rate of left-pawedness worldwide, which is 32%. So using P for the proportion of left-pawedness in Yosemite Valley, the hypotheses can be written as the null hypothesis is P is equal to 0.32. So in other words, the proportion of left-pawedness in Yosemite Valley is just the same as the proportion of left-pawedness worldwide. The alternative hypothesis would be that the proportion of left-pawedness in Yosemite Valley is greater than the proportion of left-pawedness worldwide. And just a reminder that on the homework or a test or a quiz or in your own research, you typically just have to write your hypothesis using symbols like this. You don't necessarily have to write a hypothesis as a full sentence. But in the notes, I have written these as sentences for clarity in case you would like to read the meaning of those hypotheses. We'll go on to step 2. Step 2 is to verify the requirements for this hypothesis test. And for this lecture video, I won't go into detail on verifying these requirements. It's very similar to the first example that we did in the first 2 videos. I'm going to go on to step 3, which is to test the hypotheses. And again, there are 2 or sometimes 3 main approaches to testing these hypotheses. I'm going to show all of the approaches, and it's up to you as to which approach you prefer to use. The first one we'll look at is the classical approach, or the test statistic approach. In this approach, the first thing you do is to sketch the normal probability curve and then use a table to find the cutoff value for the region that represents unusual outcomes. We'll want to note that this is a right-tail test because the alternative hypothesis is involving a greater than. We'll also want to note that alpha is 0.01. That's the level of significance. And that's also the area under the right tail of the curve. When you are working this out, it really does help to draw out that curve. So you would draw this curve, the cutoff would be on the right tail of the curve, and you're looking for this cutoff value, this z value. And to find that, go to table 5c, which is at the bottom of table 5. Here's table 5c. This is a right tail test. The alpha is 0.01, and so the z is 2.33. So that is the cutoff value for that tail, 2.33. The next thing that you want to do is calculate the test statistic. Here's the formula again for the test statistic. Remember that p sub 0 is the value of the null hypothesis proportion. N is the sample size. The p hat, we calculated that a few minutes ago. It's 0.432. Put those values into the formula and it comes out to 2.68. Now that you have the test statistic, the last thing is that you'll want to determine whether that test statistic is inside the critical tail of the curve or outside the critical tail. In this case, inside the tail would mean that it's some value on this side to the right of our cutoff, and then outside the tail would be if it was on this side to the left of the cutoff. And just as a reminder, if our test statistic is inside the tail, that means that our results are significant and unusual, and we would reject the null hypothesis. If the test statistic is outside the tail, if it's on this side, that means that the results are not significant and you would not reject the null hypothesis. So for this study, again, our test statistic was calculated to be 2.68. Here is 0 on the curve. The cutoff is 2.33. So 2.68 is inside that critical area. It is inside the tail, and that means that our study's results are significant, and we would reject the null hypothesis. reject the null hypothesis. In other words, we are ruling out the null hypothesis, and because that's ruled out, by default that gives support to the alternative hypothesis. The second approach would be the p-value approach. Here again is the definition of a p-value. I'm going to go right to the step of calculating the p-value. To calculate the p-value on a Casio calculator or a TI calculator, you would follow these steps. This time, on the Casio where it says prop, you'll put greater than, because the alternative hypothesis has a greater than symbol. .32 is the value of the null hypothesis proportion, and then 54 and 125 are the x and the n. On the TI calculator, you would follow these steps. Again, make sure to put in the greater than for your inequality of the alternative hypothesis. The p-value comes out to 3.63e negative 0.3. Remember that this stands for scientific notation. The e negative 0.3 means times 10 to the negative third power. So the meaning of that is 3.63 times 10 to the negative third. If you convert that to a decimal, that's 0.00363. So what's the meaning of this p-value? So the definition of a p-value, in other words, the definition of this number here, is that 0.0363 is the probability that 54 out of 125 randomly selected tree squirrels in Yosemite Valley would be left pod, assuming that the null hypothesis, that p equals 0.32, is true. In other words, assuming that the rate of left podness among tree squirrels in Yosemite Valley is the same as the worldwide rate of left podness, which is 32%. So now that you have the p-value, you would compare that to the level of significance, or the alpha. And remember that these comparisons are always going to be true. If your p-value is less than alpha, then that means your results are significant and you reject the null hypothesis. If the p-value is greater than alpha, then that means your results are not significant and you do not reject the null hypothesis. For this study, our p-value was 0.00363. The alpha was 0.01. That means that the p-value is less than alpha. And since the p-value is less than alpha, that means that our results are unusual and significant, and therefore we reject the null hypothesis. Step 4 would be to state the conclusion, and again, this conclusion is going to be stated in terms of the alternative hypothesis. So here's our conclusion. We reject the null hypothesis. There is sufficient evidence to conclude that the rate of left podness among tree squirrels in Yosemite Valley is higher than the rate of left podness among tree squirrels worldwide. And to clarify the connection between rejecting the null hypothesis and having this conclusion, I went ahead and wrote out our hypotheses here. We concluded that from this p-value and from the other method that we would reject the null hypothesis because the results of our study are significant. When you reject the null hypothesis, that means that, in effect, you're ruling out that null hypothesis. You're ruling it out and saying that it's probably not true. And by default, it means that you're finding support for the alternative. And that's what you're saying in this conclusion, that we're rejecting the null hypothesis, and we're concluding that there is enough evidence to support the alternative that the rate of left podness in Yosemite Valley is greater than the rate worldwide.